We see your presentation.
Perfect. Yes, thank you very much for the kind introduction and also the possibility to hold this talk here in this conference despite the current situation. Thank you very much. Yes, I would like to welcome you all on my behalf to my presentation entitled Cryopreserving Tissue Engineered Scaffolds within Cryobags. To myself, I'm a PhD student at the Institute for Multiphase Processes at the Leibniz University in Germany. And yes, before I give you insights into our study, I would like to emphasize on a few basics. Now, one of the current challenges within regenerative medicine is to regenerate tissue defects, which can origin through trauma or degenerative processes. Now, assuming that we have a sufficient substitute, the next challenge is how can we enable a long-term storage in order to enable an off-the-shelf availability. Now, in regard to the first challenge, tissue engineered constructs are a promising substitute where cells are seeded onto scaffolds, creating a tissue engineered construct, which can be aided also by biological factors. Now, these can serve as possible substitute or also as in vitro test beds. This still leaves, though, the problem, how do we preserve these structures? Now, cryopreservation enables a long-term storage. And as we all know, cell damage can occur, though, due to set wrong parameters. In that respect, we have to use also cryoprotective agents to enable a higher post-thaw viability and also to reduce the possible cell damages, even though, of course, some of the substances are toxic. Another influence onto the cryopreservation outcome is the storage container, which majorly influences the heat transfer. Now, currently, cryovials are the most used storage container, although due to their cylindric geometry and also relatively high thickness of the material, they do not have an ideal heat transfer, which is not homogeneous. Relatively new cryobags are a possible solution to that due to their flat structure to increase the heat transfer. In this regard, we focused on the cryopreservation of tissue engineered scaffolds within these cryobags and also utilized different CPAs. For that, we fabricated our scaffolds by electrospinning, by dissolving polycaprolactone and polylactic acid, both biodegradable polymers, in trifluoroethanol. And we spun this polymeric solution with our electrospinning device and received fiber mats with an approximate thickness of 100 micrometers. We punched the scaffolds out of these fiber mats with a diameter of 60 millimeters. And prior to cell seeding, we sterilized the scaffolds with UV and then seeded them with SARS-2 cells at a density of 50,000 cells per square centimeter, following 3 days incubation in an incubator. With regard to cryopreservation, which was then performed on the 3rd day, we've chosen 4 different CPA solutions, among them DMSO, which is of course the current gold standard. We applied a loading time of 10 minutes. And following that, we froze the samples within the cryobags in air in a controlled rate freezer with 1 Kelvin per minute to minus 100 degrees centigrade, following a plunge into liquid nitrogen and storage at minus 140 degrees in a cryogenic freezer. At a later stage, we thawed the samples in a water bath for 15 seconds. We removed the residual CPAs and added a new fresh culture medium, and the cell-seeded scaffolds were then recultivated for 24 hours again. Following that, we performed imaging with fluorescence microscopy and then the analysis of the obtained images in view of the viability. For that, we performed the imaging prior to cryopreservation on day 3 and also 24 hours post-thaw. We applied calcium AM for the live cells here in green, and ethidium homodimer for the dead cells here in red. And then we calculated from these images the viability as the ratio of the number of live cells to the number of total cells. Now, with regards to the results, prior to cryopreservation, we enabled viability of 97%, which then served as a control in comparison to our post-thaw results. Now, 24 hours post-thaw obviously reduced viability, and here ethylene glycol enabled the highest viability of around 80%, so it can serve as a possible alternative to DMSO, which of course known to be toxic above 4 degrees centigrade. Additionally, here not shown, sucrose can also have an impact on the viability and enhance viability under certain circumstances. What we could also see, unfortunately, is susceptibility of the cryobags to rupture upon thawing due to the high thermal gradient. Some of the bags ruptured and caused the infiltration of the water bath medium, leading to cell death. We could avoid that by using a separate container situated within the water bath filled with PBS at 37 degrees centigrade. Now, on the basis of these results, we could then compare our results to a previous study where we cryopreserved scaffolds within multi-well plates. And dependent upon cell culture duration, we could achieve here higher viabilities for the cryobags, and therefore the heat transfer seems to be improved. And another big advantage, of course, is that these cryobags are customizable to the specific sample shape and geometry, so to the sample specifications. So to conclude, the cryobags obviously improve the heat transfer and therefore the post-thaw viability, and could therefore serve as a future alternative storage container. Furthermore, ethylene glycol can also serve as a possible alternative to DMSO. And outlooking, of course, there is further potential for variation on the CPA, especially also what the loading time is concerned with sucrose, for example, but also, which is new at our institute in view of electroporation. Additional measurements are also under investigation, where we try to quantify the heat transfer with thermal sensors and perform modeling. Of course, the transferability of the method is also has to be looked at, since we used here SARS-2 cells, and in the further progress we want to switch to MSCs. So obviously every cell type has their unique protocol, so there's some adjustments to be done. And of course, the susceptibility of the cryobags to rupture has to be further investigated in order to enable a safe and secure new method for cryopreserving tissue-engineered scaffolds. I'd like to thank you for your attention, and I'm looking forward to your questions.
Let's thanks to speaker for the interesting presentation, and I'm sure that he will answer a question with great pleasure. Please, questions. Oh, questions from chat from Brian Grout. Sven, do you have a control so we will take in when constructs were treated and cooled but above a likely ice nucleation temperature?
Yeah, well, we didn't take any controls after thawing or anything. Of course, the control was then, well, our aim is, of course, to achieve the highest possible viability. That is why we used the control, which we had prior to cryopreservation, because our aim is, of course, to have as little as possible loss of our cells on the constructs. And according to nucleation, of course, yeah, nucleation, we didn't induce any nucleation, so it was just the normal heterogeneous nucleation, because it was difficult to control the nucleation within the cryogenic controlled rate freezer, due to room to actively have an influence on that.
Thank you. And Brian